that we got yeah, yeah, I think I can uh okay. Let's see if we can reduce. Yeah, I can see that one. Yeah. Plus 2x1 x2. The problem with this Lyapunov function too is that x1 x2 can be either positive or negative. So uh, from the solution, what they have given is uh, x1 4x1 square. That is it, right? 2x1 x2 plus 2x2 square. So this can be positive or negative. So to perform the Lyapunov analysis, we should be equal to 0 at x1 x2 0 and otherwise. So I'm not sure even if that Lyapunov function makes sense. Okay, just one second. Uh, okay, but this was fine. So let's see if we can reduce this one to something. Um, okay, so v dot is 2x1 x2 minus 2x2 square minus 2x2 x1 cube. Okay. Um, so, this becomes 1 minus x1 square. Alright. I'm just trying to show if this v dot can be written as something like this. Maybe with some constants. So this is v dot. Um, this is what you got as v dot, right? This is correct. Okay, so yeah, I think there is a problem somewhere. Sorry. Yes, yeah. Any positive definite v, but they have considered extra terms in that one. Yeah. Okay. Okay. Yeah. Yeah. You mentioned that last time too. Okay. So I think I'll ask about this again. This is important. Yeah. I think even that v which they have given is only positive definite in some domain. because x1 x2 can be positive or negative, so I think they're assuming something already. Yeah, that's a good point. Okay, I'll ask about this and then post on the discussion forum. Maybe they'll change the grading. Sorry. uh, yeah, I'll ask them about this question, and if it is possible then I'll let you know. Because the solution that is given is also not possible. Yeah. Okay. All right. Then, so these were the topics discussed in the last lecture week. Let's see. So first one is evaluation of the state transition matrix. So we have already seen a method which contains Laplace inverse of Si minus A inverse. Other methods are finding out state transition matrix using diagonalization, and the other one is using the Cayley-Hamilton theorem. So other than that, there are also some other applications of Cayley-Hamilton theorem. So I think one of them is to find A inverse. Others are finding some function of f such as maybe some parts of A and so on. And so this, and then we have the concept of controllability. So in controllability, we have the Kalman's test, Gilbert's test for state controllability. So this is for state controllability, and then we also have something called output controllability. Alright, so let's begin. So this is first evaluation using similarity transformation. Okay, so recall that to find the state transition matrix or e to the power at, we have to find the modal matrix P or M, and then consider P e to the power lambda t, P inverse. So e to the power lambda t for distinct eigenvalues is simply e to the power lambda 1t till e to the power lambda nt for a system with n states. Okay, so let's see. So consider the system x dot equals 0, 1, minus 2, minus 3 and an initial condition 0, 1. So to find the solution of the system, we need to find the state transition matrix e to the power at, and we'll find this using the similarity transformation. So let's find the eigenvalues first. the eigenvalues would be given by the determinant of A minus lambda I. This is minus lambda 1, minus 2, minus 3, minus lambda equals 0. So just expand this, minus 3 minus lambda plus 2 equals 0, which gives us lambda square plus 3 lambda plus 2 equals 0. Okay, so the eigenvalues are therefore, one of them is minus 1. So let's check. Yeah, and the other one is plus 2. So the eigenvalues are 1 and 2. Sorry, minus 1 and minus 2. And now we need to find the eigenvectors associated with each of them so we can find out the matrix P. Alright, so let's begin. For lambda equals minus 1, we need to calculate A minus lambda I V1 V2 equals 0. So this becomes 1 1 minus 2 and then minus 3 plus 1. So there is only one equation, which is V1 plus V2 equals 0 or V1 equals minus V2. So the eigenvector could be 1 minus 1 transpose. Alright, similarly we have the eigenvector for lambda equals minus 2. So E minus lambda becomes 2 1 minus 2 and minus 3 plus 2. So again there is only one equation, 2v1 plus v2 equals 0 or v2 equals minus 2v1. So choice of the eigenvector can be this is 1 and this is minus 2. So we have the P matrix now, the eigenvector for 1 and the eigenvector for minus 1 and the eigenvector for minus 2. So this is a simple second order system, so we know how to calculate the inverse. The determinant is minus 2 plus 1. We interchange the diagonal elements and reverse these signs. So this is just minus 1. Alright. So then what is e to the power 80? So it's p times e to the power lambda d p inverse. Okay, so let's calculate this now. This is straightforward. 1 1 minus 1 minus 2 e to the power minus t e to the power minus 2t, and then 0 is there. Then we have minus 1 minus 1. Okay, so let's see. This is just e to the power minus t e to the power minus 2t. Okay, and then we have 2 e to the power minus t plus e to the power minus 2t. We have e to the power minus t minus e to the power minus 2t. Then okay, so you have found out the state transition matrix, and therefore the solution at any time t is going to be e to the power 80 times x naught. So x naught is already given, that is 0, 1. So this is simply this column, right? So I'm just going to write this down. Yeah. So if this is clear, let's move on to the next question. Okay, so we have a state transition. Okay, so find e to the power 80 for x1 dot x2 dot equals 0, 1, 0, minus 2, x1, x2. Given the initial condition as 1, 0. Okay, so find e to the power 80 is the canonical transformation method. Okay, so this is a simple second order system, so let's calculate the characteristic equation and equate it to 0. Alright, so this is minus lambda minus 2 minus lambda 1 0. So we have the eigenvalues are lambda equals 0 and lambda equals minus 2. So let's find out the eigenvector for lambda equals 0. This is uh, e minus lambda I times the vector v1 v2. So for this we have 0 1 0 minus 2 v1 v2 equals 0. So we just have one condition that v2 should be 0. So the eigenvector is, for example, 1 0 transpose. Similarly, for lambda equals minus 2, a minus lambda I v1 v2 equals 0. So this becomes 2 1 0 1. So this is 0. So you can see we just have one equation because this row is completely 0. So we have 2v1 plus v2 equals 0, which means that v2 is minus 2 of v1. So the eigenvector is 1 minus 2 transpose. So you already know now that the modal matrix is going to be, so P inverse becomes 1 over minus 2. Okay, so let's keep it like this, half, which becomes 2 1 0 1 minus 1. Okay, so then what's the state transition matrix? It becomes 1 1 0 minus 2 times e to the power 0 t is 1, e to the power minus 2t, and then you have zeros. So this is half times 2 1 0 minus 1. So we get this and this. So this is half times 2 Then we have 1 minus e to the power minus 2t, then it's 0, and we have 2 into e to the power minus 2t. So what's the solution at any time t? So we have the initial conditions already, that is 1, 0. So this is simply the first column. So let's see, right? So this times 1, 0. Yeah. So this is a constant. 1, 0. Sorry. So if we have the given system described by x dot equals 80, where a has been given with the initial conditions 1, 0, then the state at any time t is just 0, 1. I think it's still 1, 0. So starting from the, for example, this is in R2, you are somewhere here, and for all time t, the solution remains as the initial one. Okay, so you can do this similarly for a third order system in which you need to find out the eigen values of the system, then eigenvectors. Then you proceed on to find what is P, and then you just simply calculate e to the power 80. So let me just write down the question. So we have the system x dot equals 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6 times x plus, so this is a non-homogeneous system, and the output is the first state, and we have the initial conditions already given. So this is 0, 0, 2, and u is the step input. So I think you can observe that the A matrix is in CCF form. Therefore, we already know what the model matrix is going to look like. So it is going to be, let's see, 1, 1, 1, and then it is lambda 1, lambda 2, lambda 3, lambda 1 square, lambda 2 square, lambda 3 square. So you just have to determine what the eigenvalues are. After that, we can compute what P inverse is, and then finally e to the power 8. So this is simply for distinct eigenvalues, lambda 1, lambda 2, 1, lambda 3. So let's check if the system has distinct eigenvalues or not. So e to the power minus lambda I is okay. So let's check now. Uh, this is 6 lambda plus lambda square plus 11 minus 1. So this goes away. We have plus 6. Let me write this one again. 1, 0 and minus lambda. Yeah. So this becomes lambda cube minus 6 lambda square minus 11 lambda minus 6 equals 0. Okay, so now let's see if lambda equals minus 1 solves this problem, solves this equation. So this is minus 1, minus 6, this is plus 11 and minus 6, right? Okay, so it is not that. So lambda equals 1 is 1 minus 6 minus lambda minus 6. This solves the problem. So we have, just a second. So we have lambda cube minus 6 lambda square minus 11 lambda minus 6. So this is lambda square. Then we have minus 5 lambda. So this becomes minus 5 lambda square. So there is some error here. Let me just check once. Alright, then we have, okay, so this was minus lambda cube there. Yeah. So the equation is lambda cube plus 6 lambda square plus 11 lambda plus 6 equals 0. And now I think we can substitute minus 1. So this is minus 1 plus 6 minus lambda plus 6. Yeah. So then we have to calculate this again. So one of the roots is lambda plus 1. We get 5 lambda square plus 11 lambda plus 6. Then we have 5 lambda again. 5 lambda plus 5 lambda. We have lambda plus 1. Lambda square plus 5 lambda plus 6 equals 0. So from here lambda is minus 5 plus minus upon 2. So this is minus 5. Okay. Alright, so we have distinct eigenvalues. Lambdas are minus 1, minus 2, minus 3. So you can substitute this here in P, and then you can compute P inverse, and finally e to the power 8. Alright, so the next topic is evaluation of the state transition matrix using Cayley-Hamilton theorem. So this also includes the second part, in which I've mentioned this in the overview. I think it's computation of the inverse of a matrix and some polynomials of A also. Alright, so what's the statement of the Cayley-Hamilton theorem? That every matrix satisfies, so we are talking about a square matrix in our case, its characteristic equation. Alright, so let's see. So let's consider that there was a matrix A and the characteristic equation for that was lambda squared plus 3 lambda plus 2 equals 0. So we have seen this characteristic equation before. So the question is to determine various powers of a square, a cube, for example a4 and also a inverse. So this is just a second order system, so you can compute a square, a cube, a4 quite easily. So the purpose of this question is to see how we can calculate these using the characteristic equation. So let's see. Substitute the matrix A in the characteristic equation. So we get a square plus 3a plus 2 times I, so that this summation makes sense. It's equal to 0. So what's a square then? A square is simply minus 3a plus 2. The negative of this. Then a cube is simply, so after calculating a square, you just multiply it by a. And similarly, you know how to compute a4. So we can actually reduce this further. So we have a cube equals minus 3a square plus 2i. This is minus 3 times minus 3a minus 2i plus 2i. So the goal is not to use higher powers of a other than those given in the characteristic equation. Let's see, this becomes 9a plus 6i plus 2i. This becomes 9a plus 8i. So let me just check once again. Okay, so this is minus 3a squared. Sorry about this. Now let's see. This is minus 3, minus 3a, and this becomes minus 2i, minus 2a. Alright, so we have 9a plus 6i minus 2a. This is 7a plus 6i. So a4 is now a times a cube. So we have this expression. Let's compute this. 7a square plus 6a, and let's substitute a square from the characteristic equation. This is minus 3a minus 2i plus 6a. So this is simply minus 15a minus 14i. Alright. And now we have to compute the inverse. So let's write down the equation again. It's a square plus 3a plus 2i equals 0. So on 3 multiplying by a inverse. So note that we have assumed here that a inverse exists. That is, determinant of a is non-zero. So if you have been given the matrix A, you can check first if determinant is non-zero, and then you can conclude that A inverse will exist. Then we can find A inverse from the Cayley-Hamilton theorem like this. So we pre-multiply by A inverse. So this is still 0. The first term is simply A. Then we have 3i plus 2a inverse equals 0. So this is so A inverse is simply half of A plus 3i with the negative sign. So given the 2 by 2 matrix A, you can substitute here and find out what is A inverse. Alright, so let's look at the next question. This is question 4. Yeah. So you have to find this polynomial. So this is a to the power 4 plus a cube plus a square plus a plus identity if the matrix A is given as 0, 1, minus 2, minus 3. Okay, so in the previous step, we have already shown how to compute A4 and A3. So let me just write this down. A4 was a to the power 4 was minus 15a minus 14i, and then a cube was 7a plus 6i, and a square was from the characteristic equation. So this was minus of 3a minus 2i. So given this matrix A, you can find out what A4, A cubed and A square are, and then substitute them back in this polynomial n. So let's see. A4 is minus 15a minus 14i, and 7a plus 6i, and we have minus 3a minus 2i plus a plus I. So this becomes, let's see, a is minus 15 plus 7 minus 3 plus 1. And the coefficients of identity matrix are minus 14 plus 6 minus 2 and plus 1. Okay, so now let's compute. This is 8 and 18. So minus 10a. Yes, and this is 7 uh, minus 7, and then we have minus 9. So now the only thing that we have to do is substitute the matrix A. Minus 9 times 1, 0, 0, 1. So this is minus 9. Then we have minus 10, 20, and then we have 30 minus 9. So you can see how easy it was to compute these higher order polynomials that we would have otherwise calculated by multiplying a n times, right? Alright, so this is clear. Let's move on to the next one. So you have to recall some concepts there before we begin. Okay. So you already know that the characteristic equation I am going to denote by the function of lambda. This is delta of lambda. So this is lambda I minus a or a minus lambda, and this is nothing but lambda to the power n plus lambda to the power n minus 1, so on till alpha n. So this is the characteristic polynomial. And according to the Cayley-Hamilton theorem, the matrix A would also satisfy this. So we have a to the power n plus a to the power n minus 1 till alpha n equals 0. Sorry, alpha n times I. Okay. So this theorem provides a simple procedure for evaluating the function of a matrix. So for example, the function of a matrix denoted by f of a is given by something like alpha naught I plus alpha 1a plus alpha 2a square, so on till alpha n a to the power n, and then so on. Okay. So the scalar polynomial f of lambda is given, let's say that this is something a naught plus a1 lambda plus a2 lambda square n lambda n, and so on. Okay. So then we can divide the by characteristic polynomial. Let's see, f lambda over delta lambda, and let's say this is given by some question. Sorry about this. This is given by some question in terms of lambda plus some function g lambda over delta lambda. Alright. So where g lambda is the remainder, and the remainder is going to be of the form a degree less than n, right? So let's say there are some coefficients beta, so beta naught lambda 1, so on up to beta n n minus 1 lambda n minus 1. Okay. Now this equation, we can rewrite this as f of lambda equals q lambda delta lambda plus g lambda. So let's assume that there are distinct eigenvalues. So let's say these are n eigenvalues for an nth order system. We have lambda 1 till lambda n, and let's say so if these are the eigenvalues, then the characteristic equation at any of these lambdas is going to be exactly 0, because that's the definition of eigenvalues, right? These are the roots of the characteristic equation. Okay. So then f at any lambda I is simply going to be g of any lambda at the same eigenvalue. Okay. So we have some f lambdas which is given in the coefficient a0, a1, so on, and these g's are in terms of the scalars beta n minus 1. Okay. So these set of scalars can be determined by the n equations. Which are these n equations? F lambda equals g lambda I for each distinct eigenvalue. Says eigenvalue. Okay, so you now know what g of lambda I is. Okay, and so you can substitute a in terms of lambda. So again we have f of a equals qa delta a plus g times a. Okay, so you know what this is and what this is. Okay, so this at the characteristic equation, if we substitute a, this is 0, then we have f of a is simply g of. So what we are after is the remainder, right? We need to calculate the coefficients in the remainder polynomial to compute the polynomial f of a. Okay. So this was the case for distinct eigenvalues. So there is another case which is for repeated eigenvalues. So let's say that there is an eigenvalue, some lambda k, which is repeated, let's say mk times. Okay, so to compute the polynomial f of a, what we have to do is we have to solve for beta so that we can get g of a, right? So I'm going to write down the steps first. So how do you find betas? So one of those betas is going to be when you just substitute this lambda for the first time, and then this is repeated mk minus 1 times. So then you can find out those betas as d lambda j. You differentiate the characteristic polynomial, evaluate it at lambda k, and put it to 0. So j actually goes from mk minus 1. Alright. So if this is alright, so for repeated eigenvalues, this actually reduces to lambda to the power j. F of lambda evaluated at lambda k is exactly equal to, sorry, this is the gth order differentiation of g of lambda evaluated at lambda equals lambda k. So this is how you find the coefficients beta with respect to the repeated eigenvalues lambda k. And then you can just solve for those unknown beta n's. So beta 0, beta 1 up to beta n minus 1, and say that f at a is g at a, and this is simply, sorry, beta n minus 1 lambda n minus 1. Okay, so let's look at a question first. So this is, I guess, sixth question. Let me check. Yeah. Okay. So we have a square matrix, 0, 1, minus 2, minus 3. Okay. So to find out the polynomial a to the power 10, what we can do is find out the characteristic equation first. So what's the characteristic equation? Let's see. This is simply 3 lambda plus lambda squared plus 2 equals 0, or lambda square plus 3 lambda plus 2 equals 0. So this is delta lambda equals 0. So according to the Cayley-Hamilton theorem, we have a square plus 3a plus 2i equals 0. Alright. Also, what are the eigenvalues? So let's check if these are distinct or repeated. So we have already calculated this several times. This is minus 1 and minus 2. So we are in the simple case right now. Distinct eigenvalues. Alright. So what's the order of the matrix A, or order of the system? It's 2, right? So G lambda is the remainder term. So it is going to have beta 0 I plus beta 1 A. Okay, so we have to calculate f of A, which is exactly G of A. Sorry, what is this? Is just lambda, and this is equal to B0 times identity plus B1 times A. So the goal is to find the coefficients beta naught and beta 1. Okay, so how do we do that? So f at lambda 1 is G at lambda 1. So f at lambda 1 is simply lambda 1 to the power 10 equals B0 plus B1 lambda. So you already know what the eigenvalue is, so minus 1 to the power 10. So this is going to be simply 1 equals beta 0 minus beta 1, or beta naught is 1 plus beta 1. Okay. So we have two unknowns, beta naught and beta 1. So we need a second equation as well. So for lambda equals minus 2, we have minus 2 to the power 10 equals beta naught minus 2 beta 1. So let's substitute 1 plus beta 1 minus 2 beta 1 minus beta 1. So beta 1 becomes 1 minus 2 to the power 10. So you can calculate this. This comes out to be minus 1022. And this means that beta 0 is simply 1 plus. Alright. So this is minus 1023. So you can check the calculations once, or I think I made a mistake. Yeah, this is minus 1023, and this is simply 102 to the power 10. Okay, so now f at a, which is a to the power 10, is simply minus 1022 times identity, minus 1023 times the matrix A. So you can substitute A and identity here. So I'm just going to write down the final answer. This is minus 1022 minus 1023. So you have found this large power of A without multiplying the matrix 10 times. Okay. So now we have calculated the general function f of A. So this means if f of A is the state transition matrix or e to the power at, you already know what this is, right? I plus at plus e square to factorial and so on. So now we need to find f of A using this function evaluation approach. So we need to find out what g of A is. Okay, so let's see. Just one second. Yeah. So consider the system x dot equals ax with a given by 0 0 minus 2 0 1 0 1 0 and 3. The third order system with an initial condition 0 1 0, and the goal is to find out f of a equals e to the power at using the Cayley-Hamilton theorem. Alright, so let's see. The first step is to compute the characteristic polynomial. So we have a minus lambda I equals 0. This is nothing but, so I'm just going to write this down. This is given by lambda 1 minus 1 squared, lambda minus 2. So you can compute this. Okay, so what are the roots? We have repeated roots 1, 1, and then we have a distinct diagonal. So this is the case of repeated eigenvalues. And now we'll see how to compute that function g or those coefficients beta in the case of repeated eigenvalues. Okay, so A is of third order. So the remainder polynomial is going to look like beta 0 plus beta 1 lambda plus beta 2 lambda square. So this is the remainder polynomial. So what do we want to calculate? We want to calculate g of lambda such that when we have these coefficients b0, b1 and b2, we can find out what g of a is, and we already know that f of a is g of a. So we would have found out what the state transition matrix is going to be. Okay, so this is the goal. Now let's see. So f of lambda 1 is g of lambda 1. So, and since we have repeated eigenvalues, the first one, then we have d by, let's say, d lambda of f, which which is a function of lambda evaluated at -1, is exactly going to be equal to derivative of g evaluated at -1, and then we have f of lambda 2 equals g of lambda 2. So here lambda 1 is -1, lambda 2 is, sorry, it's just positive. Okay, so let's conclude these. E to the power lambda 1 t is e to the power minus t. This is going to be beta naught plus beta 1 plus beta 2. Similarly, you differentiate the function f of lambda equals e to the power lambda t and evaluate it at -1. So minus t e to the power minus t, because you are differentiating f with respect to lambda. Okay, so sorry, this is 1, and then we have beta 1 plus 2 beta 2. Okay. So d by d lambda, g lambda is simply beta 1 plus 2 beta 2 lambda, and we evaluated this at 1. And then we simply have e to the power 2t equals beta 0 plus 2 beta 1 plus 4 beta 2. This is positive. Okay, so these are three equations and three unknowns, which are beta naught, beta 1 and beta 2. Okay, so you can solve this equation. So you already know how to do this, right? So you form this matrix beta 0, beta 1, beta 2. You have this e to the power t. We have 1, 1, 1, 0, 1, 2, 0, 2, and 4. So for example, let's say this is some x, then this vector is going to be x inverse times this. So just check if this matrix X is invertible and then compute X inverse to find beta 0, beta 1, beta 2, beta 2. Alright. So I'm going to write down what are the values of this. So you can check these later. And finally we have e to the power 2t minus e to the power t, e to the power t. Okay. So now we are almost done. We need to find f of a, which is e to the power 8t. So we need to find g of a. So g of a is beta 0 times identity plus beta 1 times a plus beta 2 times a square. So we already know what a square is, right? You can either multiply a, or from the characteristic equation you can find out what a square should be. Okay, so you can substitute this and get e to the power 80. This is going to be a 3 by 3 matrix. So you can already see what are the terms are going to look like. For example, the first term is going to be beta 0 times 1. So something like 2t to the power t minus plus e to the power 2t, and so on. So I'm going to write down the final expression. So this comes out to be 2e to the power t minus e to the power 2t, 0 minus e to 2t, then you have 0, e to the power t 0, and then again 2e to the power 2t minus e to the power t. So we also know some initial condition. We have been given those. So it is x0, let's see, Okay, so 0, 1, 0. So what we are actually doing is just extracting this second row and writing it as a column, right? You can check this if you multiply this matrix by 0, 1, 0. So this is 0 e to the power t and 0. Or sorry about this, extracting the second row, second column of this matrix. So this is fine. Let's move on to the next question. So we have to find e to the power at. Just a second. For a simple system, so for a equals 0, 1, minus 6 and minus 5. So there are various ways you can do this. You can use Cayley-Hamilton theorem. So let's see the eigenvalues first. So a minus lambda I is minus 5 minus 5 minus lambda 1 and minus 6. This becomes 5 lambda plus lambda squared plus 6 equals 0. So the characteristic equation is, or the characteristic polynomial plus 6 equals. So according to the Cayley-Hamilton theorem, we have a squared plus 5a plus 6i equals 0. Alright, so you need this function evaluation. So you need actually the remainder polynomial evaluated at a and at any lambda we have for a second order system beta 0 plus beta 1 lambda. You already know what to do, right? We can just find out if the eigenvalues are distinct or not. So what are the eigenvalues? Lambda equals minus 1. Let's see. 1 minus 5 plus 6. Right? So the second order one, you can just compute this directly. Okay, so these are, minus 5 plus minus 1 over 2. So this is minus 2 and minus 3. We have distinct eigenvalues. Okay, so you have two eigenvalues. Let's substitute in G lambda. So G lambda 1 is beta 0 minus 2 beta 1. This is f of lambda 1, which is simply e to the power minus 2. Similarly, we have G lambda 2 equals b0 minus 3 1. This is e to the power minus 3. So you can find out what beta 0 and beta 1 are and finally compute what is going to be e to the power 80. This is beta 0 plus beta 1 80. Okay. So let's move on to the next topic, which is controllability. Okay, so recall that we had two tests. First one was okay, so computation of the Kalman matrix, which was B AB A square B, okay, e to the power n minus 1 B for an nth order system. Okay, so the rank of this matrix, let's see, this is the controllability matrix. A rank of this controllability matrix should be n. So for this is for the pair AB to be controlled. Alright. And the next one was the request test. So according to that test, the first step was uh, to diagonalize the system. So we had that transformation using the modal matrix P. We can diagonalize the system. Then the next step was, so we had that A tilde, which was basically lambdas on the diagonal, and you have B tilde. So I'm assuming that this was M inverse or B inverse times B, and you had this column vector. Okay, so how do you check then if the system is controllable? So the system is controllable if all the elements of this B tilde matrix, B tilde vector were non-zero, and if any of them were zero, so that meant that that particular state was not controllable, and hence the whole system is not controllable. So let's start with some simple questions. Question 9. Yeah. So for controllability, we just need the matrix A and the vector B, or the matrix B. So determine the controllability of the following systems. Alright, so the first one is the second order system. We have the matrix A and B. Let's see. Minus 2, 1, 1 minus 2, and 1, 0. Okay, so the controllability matrix is going to look like B and AB, right? Because this goes up till n minus 1. So we just need to find out what AB is. 1, 0. Alright, so this becomes minus 2 and 1. So we have 1, 0, minus 2 and 1. So to check the rank of this square matrix, what we can do is check the determinant. So what is the determinant of the controllability matrix? It's 1. So it's full rank. Rank of C is 2, which is equal to n. Therefore, the pair AB is controllable. Alright. Now let's look at a third order system. Let's see. So the matrix A is minus 1, 0, 0, 0, minus 2, 0, 0, 0, and minus 0. And we have a multi-input case. So B is a matrix here then. It's 1, 0, 1, 2, and 2, 1. Okay. So the controllability matrix is going to look like B, A, B, and A square B. So let's find these out. AB is going to be check the dimensions first. Yeah, okay. So first of all, we just have -1, then we have 0, then it's simply -2, -4, and we have -6, -3. Okay. Then we have a square b, which is a times ab. So let's calculate. Okay, so this becomes 1 and zeros everywhere else. Then we have uh, 4 and 8, 15 and we have 9. Okay, so the controllability matrix is going to be, let's see, first is just B, so 1 0 1 2 2 1, and we have AB, and we have A square. So we have 3 rows and 6 columns. Okay, so now we have to determine the rank of a matrix which is not a square matrix. So then what is rank of C? If you cannot compute determinant, it's defined as the number of linearly independent rows or columns of C. And note that this is always going to be less than equal to minimum of let's say n and m, where this C matrix is n is yeah, it contains n rows and m columns. Okay, so then what does it say? That rank of the controllability matrix is going to be at most 3, right? So if it is 3, then it's controllable. If it's anything less than 3, then it's not controllable. Okay, so let's check if these 3 rows are linearly independent. So how do you check that? So let's say there is some coefficient alpha 1 times 1 0 minus 1 0 1 0 plus alpha 2 times 1 2 minus 2 minus 4 4 8 plus alpha 3 times 2 1 minus 6 minus 3 18 and 9 equals zeros. So it's 1 2 3 4 5 and 6. Okay, so we have many equations to find out what alpha 1, alpha 2 and alpha 3 should be. So let's see. Alpha 1 plus alpha 2 plus 2 alpha 3 equals 0. Then we have minus 2 alpha 2 plus alpha 3 equals 0. Okay, so there is another 0 here. The fourth one. Minus 4 alpha 2 minus 3 alpha 3 equals 0. Okay, so these are distinct equations. You can find out what alpha 2 and alpha 3 are. Then substitute those here to find out what alpha 1 is. Now, if alpha 1, alpha 2 and alpha 3 are 0, then the 3 rows are linearly dependent. Then the rank of C is also 3 and the system AB is controllable. However, if any of those lambdas is non-zero, alpha 1 is non-zero or alpha 2 is non-zero or alpha 3 is non-zero or any combination of this, then rank of C is less than 3 and the pair AB is not controllable. Okay, so you can check this. Compute the values of alpha 1, alpha 2, alpha 3, comment on the rank and the controllability of the system. So we have already looked at the Gilbert's test. So let's see. So I'm going to write down some systems which have already been diagonalized. And we just need to check if those systems are controllable or not. Okay, so let's see. The first system is -1, 0, 0, -2, okay. So this is the diagonalized system. How do you do? This A matrix is a diagonal matrix. Okay, so both of them are non-zero, therefore it is controllable. Okay. Now we have a third order system. Let's consider that there were some repeated eigenvalues for the system. So we will have Jordan blocks. So let's say, sorry, this is not a third order system, a fifth order system. And the eigenvalue -2 was repeated 3 times. So the Jordan block for that is going to be this and this, right? This is the Jordan block. So there are 3 eigenvalues, then you have zeros everywhere. See, zeros here also. And then you have 2 repeated eigenvalues at -5. So this Jordan block is going to look like this. Then you have x1, x2, x3, x4, x5. Just remember this is going to be a 5 by 5 matrix. So, okay, so this row is not there then. Yeah. Okay. So we already have the B tilde matrix here. So this is 0, 1 for 5 states, 0, 0, 3, 0, and then 0, 0, and 2, 1. So this was a multi-input system, U1, U2. So now let's check. Okay, so in case of repeated eigenvalues, uh, in the case of repeated eigenvalues, so how do you check uh, the controllability by looking at the B tilde matrix? So the elements of any row B tilde that correspond to the last row of each Jordan block are not all zero. Then the pair AB is controllable. Alright, so let's see. So we have the first three rows are for this Jordan block, lambda equals -2, and then this is for lambda equals 5. So this is last row, this is non-zero, and this is the last row for this Jordan block. So the system is controllable. Okay, now let's look at some cases where it's not controllable. So again, the system has already been diagonalized. Yeah, so this is again a second order system. The diagonal system -1, 0, 0, -2 times x1, x2 plus the B tilde matrix, and this is 2, 0. So this is the case of distinct eigenvalues, and one of the elements of B tilde is 0. So it is not controllable. Now you have again a fifth order system, or let's say a third order system. X1 dot, x2 dot, x3 dot. So there are two repeated eigenvalues at -1. So this is the Jordan block, then 0, 0, 0, and there is one eigenvalue at -2. So this is the Jordan normal form for the A matrix. And let's say that there were two inputs, U1 and U2. So corresponding to that, the B tilde matrix was found out to be 4, 2, 0, 0, 3, 0. So for repeated eigenvalues, you have to look at the last row, and this was a distant eigenvalue, so this is non-zero. But this is 0. So it is not controllable. Okay, so I hope this was clear to you. Okay, so I think there was one more topic which I forgot to mention. It was stabilizability, right? This was done in the sixth lecture, so let me just include that. We'll also do that. Okay, so this means that we're talking about partially controllable systems. Okay, so when is it partially controllable? So you have two eigenvalues or two modes. You have those unstable modes and stable modes. So unstable modes are controllable. So if it's a growing eigenvalue, for example, e to the power t for lambda equals 1, then you can control that state. And if it's a stable eigenvalue, it's going to decay on its own without any input as well. So this may or may not be controllable. So these are uncontrollable, but these are stable modes, and unstable modes are controllable. So then the system is known to be stabilizable. So let's see. Uh, so let's consider that the system has been diagonalized. This is a second order system. So 1, 0, 0, and -1. So by modes we mean eigenvalues. So we want to talk about which of the eigenvalues are controllable and which of them are not. So we have to reduce this to a diagonalized system. So x1, x2 plus 1, 0. So these are distinct eigenvalues. So you just need to check If there is a 0 here, so there is a 0 here. So it is uncontrollable or not state controllable. Why? Because the second state x2 is uncontrollable, right? However, is it stabilizable or partially controllable? So let's see. So this eigenvalue is the stable part because this lies on the left hand side of the S plane, but this is a unstable eigenvalue or unstable mode, and its corresponding element in the B tilde matrix is non-zero. So we conclude that the unstable mode is controllable and the stable mode is uncontrollable, which implies that the system or the pair AB is stabilizable. Okay, so if you need to comment on whether a system is partially controllable or not, you can first diagonalize the system and then look at this B tilde matrix. So in the case of repeated eigenvalues, we have already seen the condition uh, when the system is controllable or when that particular state is controllable or not. That is, I think we have written this. Yeah, right. Okay. So I hope that the questions from today were clear to you. Alright, so let's stop for today. Thank you.